So we said that the derivative is a limit. And if we're going to look at limits, we're probably going to want to look at limits from both sides. So here we actually do have to consider one-sided derivatives, and this will help us talk about what it means for a derivative to maybe not exist because we know it's a limit. Okay, so if we go from the right, so if we take the limit as h approaches 0 from the right, then of f of x plus h minus f of x over h, then we're talking about the right, or sometimes called the right-handed derivative at x. If we come from the other side, from the left, the limit as x approaches 0 from the left of this difference quotient, that would be the left, or left-handed derivative of x. And we'll look closer graphically at that in a minute, what that means. So because it's a limit, it really has to do with these one-sided derivatives, their existence, and their equality. All right, so the first thing is, so if you want to talk about when a derivative exists or not, a derivative exists. The first thing you need is you need continuity. Okay, so continuity is a necessary condition for derivatives. If it's not continuous, we're going to see it's not differentiable. So that's the first thing. And then, because it's a limit, we would need the left and right derivatives to both exist and to be equal. Okay, so what does that actually mean when we're looking at a graph? Because we're not talking about the function values anymore. We're talking about this difference quotient. And what would that mean? Well, one way that we can consider this is basically we're talking about slopes of tangent lines. So when we're talking about approaching some value, so let's call this the point A here, and we want to know if the function, if the derivative exists here. Well, what we're really looking at when we're talking about the limit and we're talking about approaching A, or in other words, the h going to 0, we're talking about looking at all these tangent line slopes and what is happening to them. So basically, if these tangent line slopes move nicely and just turn a little bit and they move smoothly along this curve to that point, then we're saying that the derivative, that would be the left existing. And if we had the same thing and it was going to some slope there from the right and going nice and smoothly, transitioning from one tangent line to the next, then everything is good. And this is, in fact, differentiable, so we sometimes shorten it like that, at x equals a. Okay, so what we saw was the transition of the tangent lines was nice and smooth through that point. Okay, now look over to the right one. Okay, so here, as we're coming from the left, are the tangent lines and what they're doing. Now notice when we get really close to the point of interest here, the tangent line from the left, essentially I'm just going to rewrite it down here, is something like that. All right, now I'm going to come from the right, and these are all the, be the tangent lines. But now when I get to that point, it looks like the tangent line at that point then would be something like this. So something like that. And then if I had to move through that point, it would instantly have to transition and become over there. Not smoothly go through. It would have to make this jerky motion to all of a sudden be the next tangent line. And that's not good. Basically what we found was that the limit from the left and the limit, from the right did not end up being the same value. They both existed, but they ended up being different values. So the slopes end up being different of the tangent lines. It's not like the original limits we looked at where we were talking about basically function values being different. No, that was with functions and the limit of functions. Now we're talking about the limit of the difference quotient, so we're talking about slopes of tangents. Okay. Well, the nice thing is we basically have a bunch of things to look for to determine when a derivative might not exist. And we can list them, really. So when might a derivative not exist? Well, first, we said it has to be continuous. So if you have a discontinuity, then we're done. It can't be differentiable. Okay, so this is not differentiable at A because we obviously have this discontinuity there. That's it. Okay, the example we looked at before was an example of a sharp corner, which is not differentiable. Okay, so again, we have these derivative values that have to suddenly change at this point right here. So they both come out to be nice slopes. They're perfectly fine slopes, just they don't match. Okay, so in essence, we could say that the one-sided derivatives are not equal. And as a result, it's not differentiable at that point. Okay. A similar looking issue is a cusp. Now, it can be very difficult to draw this and see the difference, or even see the difference on a graph. So let me explain the difference here. It does look like there's a corner there, and we're often don't make too much of a big deal about distinguishing that formally between cusp and corner. I'm not going to make a big deal if you interchange them, but there is technically a difference. So with a cusp, what's happening is, as you approach the point of interest, your tangent line becomes vertical. Okay, so it's heading to become vertical in the limit. Okay, and the same thing from the other side. Okay, so these are ending up, these slopes are ending up being infinite. Okay, one of them with positive slopes and one of them with negative slopes, but they're both ending up to be infinite. So that's the problem. In this one, the one-sided derivatives go to infinity. So we basically have a limit of infinity, and so the limit doesn't exist, and so it's not differentiable there. So they're doing the same thing in that they're both going to n infinity, but technically they're not going, they're going to something that's not a limit, and so the limit doesn't exist, the derivative doesn't exist there. All right, I called that one 3a, and now let's go to what I'm calling 3b, because it has a very important connection. The real problem here is the idea of the slope going infinite. So again, this is very difficult to draw properly, but what you have to imagine is that here are the slopes, and somewhere in here, for a moment, this tangent goes vertical. So this one actually has a vertical tangent in it, whereas the previous ones, they're headed to be vertical in the limit. So it's still a vertical tangent line, and so it's an infinite slope, and that's no good. So again, we have, so from either side, the one-sided derivatives go to infinity, and so not differentiable. So those are the things that we're normally looking at. We're looking at discontinuities, sharp corners, cusps, and vertical tangents, and that's what will give us discontinuities. Let me make an important final point here. Now, we said that you have to be continuous to be differentiable, but you often hear it said that differentiability implies continuity, and that's true. if you have differentiability for whatever reason, you know you must be continuous because you're not allowed to have differentiability if it's not continuous. But what people confuse this here is they go backwards and they try to say continuity implies differentiability, but the reverse doesn't hold. Here's an example. Here at A is a perfectly continuous function. It's continuous at A, but not differentiable at A, okay? And that can happen because basically continuity is, a lower level. You're trying to get to the higher level of differentiability. So it was like limit existence was nice, but if you could get limit existence matching the function value, then you could get continuity. Now, if you have continuity and you get these nice derivatives on both sides matching up, then you can get differentiability. So it's a hierarchy of we're getting functions that have better and better properties at that point. Okay.